In this tutorial, I am going to review how we do error propagation in chemistry. We're going to look at three different ways. The hard way, which I refer to as is the memorizing a bunch of rules from a table. The easy way is the method that we use that is a little bit more general, requires a little bit of calculus. The very easy way is how we use Mathematica to do that calculus in case we forget some of our derivatives. Most of this work is based off of the material that we find in Quantitative Chemical Analysis. In the 8th edition, Appendix C gives plenty of information about how to do this. To begin with, when we make measurements in a laboratory, let's say we've measured two values, A and B, the average value may be, in this particular case, 1.76 and 1.89. However, both of those values are going to have some amount of uncertainty. If we graph that pictorially, what that means is that each value would have a central value equal to the mean, but sometimes if we measured it, we would measure a little bit higher value or a little bit smaller value. The dispersion around the central value is the standard deviation for us. And if we took these two values, the averages, on average, we should add the two together to get 3.65, but maybe sometimes we're averaging one of the higher values of A with a higher value of B, and we could get something like 3.72. So the question then becomes, when I take two values, each with uncertainty, to get a final value, what is the uncertainty in that final value? If we take a histogram, we would see that the average value is what we would expect, the average of the two real values without uncertainty, but there is also some dispersion in this particular case as well. If I graph all three together, we see that the dispersion of the answer is a little bit broader than the dispersion of either of the two original values. So we need some tools in order to figure out what this dispersion or this uncertainty is. If we talk about the hard way, we memorize a table. This table is in Chapter 3 of the 8th edition of Harris. And what we do is simply look for the operation that we're performing and find out how we calculate the uncertainty. We're doing an addition in this particular example, and so in order to find the uncertainty in y, we're going to take the uncertainties of each of the values we're adding, square them, take the square root. If we look at an example, we could take the values from the previous section, 1.76, 1.89. Each of those had these standard errors of 0.03 and 0.02. Here's our equation for adding together the squares. Take the square root, and that should give us the error. And so the error for our final answer should be 0.036 if we're adding them together. Apologize for the little disorganization here. I've also done the multiplication as well. If we take A times B, if we go back up to the table and see A times B, the only difference here, instead of adding the errors together, we're adding the relative errors together. But again, we know how to calculate a relative error, square it to get the relative error of our final answer. And in this particular case, the error, if we multiply them together, would be this 0.066 value. So this method is convenient when we use addition and subtraction, multiplication, division, or any of the functions that are presented here. But more generalized terms are going to require us to use a different approach, and more complex functions may be cumbersome using this particular method. And so let's take a look at some of the calculus that is actually used here. And the error, or the error squared, which is the variance of a function, is going to equal this this term, which at first looks really clunky, but what we're essentially saying is that the error is equal to the error squared of the individual measured value times the square of the partial differential with respect to that particular variable. We're going to add up all of those, and we get the variance. So let's start off with an example. Again, the same exact example that we've been working with before. We're taking a and adding it to b. So the function that we're doing is y equals a plus b. The very first thing we need to do is look at the right-hand side and take the partial derivative of this function with respect to anything that has error in it. So that means first we're going to take the partial differential of a plus b with respect to a, and then a plus b with respect to b. Now what's nice in this particular problem is that those partial differentials are very easy. They're both 1. So when we take a look at our error equation, we see the partial differential of y with respect to a and the partial differential with respect to b are both 1, and we're going to get ea squared plus eb squared, and that's the same thing as what we had before in the previous example. So in this particular case, using the table really is a lot more convenient than calculating using the partial differentials. We also get the same answer if we use multiplication, and in this particular case, when we take our differentials, a times b, the derivative of this with respect to a is b, and the derivative of this with respect to b is a. And I'll let you do that on your own just to convince yourself. But notice that I've done that here. I've plugged this in. And then once we plug in numbers, we're going to get the same value. And I believe, perhaps this is just my opinion, but I believe in this particular case it is easier to use use the error propagation function than remember the table, because we don't need to worry about whether or not we're using relative errors. Now at this point, if you're not interested in using Mathematica, we can go directly down to some of the exercises and view those in the PDF version. But if you are interested in Mathematica, let's take a brief look at how this is actually done in the or can be done using Mathematica. First, we're going to clear some variables and define our function as a plus b. Then we can take the derivatives of this function fairly easily by using the command d. Then we insert the name of the function and the variable that we're trying to take the derivative of. As with the previous examples, we should see that both of these derivatives are 1. Next, what we do is we need to take this function, this is our error propagation function, and convert that into format that Mathematica can understand. And this part here in the beginning is the derivative with respect to a, and notice how I put that in there, squared, and I put that in there, times the error of a squared, and I've put that in there, and then the same thing is over in this part right here. The entire function is then raised to the 1/2 power, or we take the square root, and that's where the square root comes into play. I do all of this first, and then what I do second is actually substitute the actual values into the equation. So first I see what the function is that for calculating EY, and then I plug in those values to get the same result. This method, while still requiring a little bit of user input, makes things is easy to generalize, and so we can see if our function is a times b, we set the symbol func equal to the function that we're interested in. We then use the square root equation, and then we substitute our variables to get the answers. Lastly, if you want to take a look at the way to put all of this into one function, I'll let you look at the notebook file on your own, but I give you an idea that allows us to actually create a function to propagate the error and calculate the error with one click of a button. And we see that what we end up doing is putting in our function, the variables that we're interested in, and out comes the answer. There are some exercises that I think are going to be easy enough for you to take a look at. Each one of these has the answer underneath it. I would like to see you do these and then come to me with any questions that you have.